started. So it's my great pleasure to welcome today our colloquial speaker, Dr. Jason Veatch. And so he's currently at Cal State University East Bay, where he's doing a postdoc as part of the CSU New Pack program. Before that, he was at University of Göttingen, which we discussed, is like the home of quantum mechanics. Basically, everything you study in your basic quantum mechanics books, in like say Griffiths and so forth, essentially came out of Göttingen or the Göttingen School. And then he did his PhD at University of Arizona, and that's as far as he got as academic history goes. And then I learned from Ray that he's a rock climber and also like enjoys physics toys, much like Ray. So today he's going to tell us about particle physics at CERN. Let's welcome Dr. Veatch.
Thank you very much for the opportunity to speak here. Thank you for the introduction and the invitation. So yeah, I will begin just very briefly telling you my background and path into the field. And so in 2001 was the first time I took a physics class in high school, and I was hooked. 2003 was a very critical year. We took a high school field trip to Fermilab in Chicago, and I can pinpoint that week is when I realized this is what I wanted to do with my life. I did my undergrad at University of Evansville, graduate work at University of Arizona. 2012 was when I formally joined the Atlas collaboration. Then in 2015 I moved to Göttingen, and since this year I've been at Cal State East Bay. And I'd like to point out this photo from 2018 Fermilab. I got to go back to a conference to where it all started. Okay, so back to the physics. So before we dive into the physics, I want to introduce the units we use and the scale of what all of this means to give you an idea of what actually we are talking about in terms of everyday life. So in particle physics, we use the units of giga-electron volts, or GeV, to measure both mass and energy, and momentum as well, except I'm not really going to discuss momentum today. Also, sometimes I'll refer to MeV or TeV, which are 1/1000th or 1000 GeV, respectively. To give you an idea of the scale of this for mass, a baseball has a mass of approximately 10 to the 26 GeV. So everything we're talking about, on order of 1 to 100 some odd GeV, much, much, much smaller than anything in our everyday life. And as far as energy is concerned, the kinetic energy of a typical pitch in a Major League Baseball game is about 10 to the 29 GeV. So also the energies we're talking about are much, much smaller than our everyday life. And something that is comparable is the kinetic energy of a flying mosquito. Has a kinetic energy of about 1 tera-electron volt. And so if you're looking at the LHC, each proton inside the LHC has a kinetic energy, has an energy of 6.8 tera-electron volts. To give you an idea of what this scale is. Okay. So the question we're trying to, generally trying to answer in particle physics is, what are we made of? And us and the entirety of the universe. And the answer is matter. So everyone is familiar with atoms, building blocks of everything, but atoms, of course, are not fundamental. They're made of a nucleus as well as electrons. Electrons, as far as we know, are fundamental, but the nucleus is further made up of protons, which are further made up of quarks. And as far as we know, quarks are fundamental. And so that's the beginning of the answer. What are we made of, and what is the universe made of? But there's a bit more to the story, and a very simple equation that explains all possible constituents of the universe and all possible interactions between them. So you're taking notes, right? There's a quiz on this at the end. Now this is the standard model Lagrangian. This is the equation that defines all of these interactions. Just a moment for a vote. But it can be simplified. It can be simplified, graphically like this. So this is the particle makeup of the standard model. The standard model describes everything in the universe, and all of the particles in the standard model can be split into fermions on the left and bosons on the right. Fermions are the stuff of matter. They're the things that, everything is actually made of. I talked already about the electron and quarks, in particular the up quark and the down quark, which make up protons. However, these are not the only fermions, as you can see here. If you look at the electron, you notice there are three particles in the same row: the electron, the muon, and the tau. These are the three different generations of the charged leptons. Each one is simply heavier than the previous one. Otherwise, their properties are very similar. And similarly, for the up and down quark, each one has three generations of quarks: charm, strange, and top bottom. And then finally, you have three generations of neutrinos. These make up the rest of the leptons. These are very difficult particles to work with. They do not interact with matter very easily, and therefore, in my field, we pretty much just treat them as non-detectable and don't really distinguish between the three of them. Neutrino physics is a whole other area of research which is absolutely fascinating, but in high energy physics we just kind of treat the neutrino as neutrino. On the other side are the bosons, which the four bosons over here, the Z boson, the W boson, the photon, and the gluon, are the force mediating particles. Each one is associated with a fundamental force, which I'll get to in just a little bit. And then finally is the Higgs boson, typically shown here in the center, but it is another type of boson, and I'll get into more details there. And it's probably the one that you've heard the most about, especially in the news in the last several years. Okay, so I mentioned the fundamental forces. There are four fundamental forces in the universe: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. And the force you are undoubtedly most familiar with is gravity. It is the force that keeps us on the Earth. It keeps the moon in orbit around the Earth in the orbit around the sun, etc. However, in some ways, it is the force we know the least about. It is, notice it is kind of falls out, it's indicated differently than the others. This is because we do not have a quantum mechanical description of gravity that has been verified, and therefore is not part of the standard model. The other three forces are. They're all three of them are much, much stronger than the gravitational force. The first one is the electromagnetic force. This is the force that governs, electricity, magnetism. It's what keeps electrons bound to nuclei in atoms. And the mediating particle is the photon, which is massless. Next is the weak nuclear force. This is the nuclear interaction that mediates radioactive decay or nuclear decay. The mediating particles are the W and Z bosons. These are not massless, and this comes up later. And then finally is the strong nuclear force. And this is what binds quarks together to form hadrons. Hadrons being protons and neutrons or any other bound state of quarks. And the mediating particle is the gluon, which is also massless. I keep bringing up particle masses because this is particularly relevant to the Higgs boson. So if we look at the masses of all of these different fundamental particles in the standard model, we see a very wide range of masses. And this is a bit old. Some of these numbers have changed slightly, but to first order, this is all about correct. As a reference, the mass of a proton is approximately 1 GeV. And then we have masses, say the neutrinos, which are almost zero, to the electron, which is half a mega electron volt, all the way up to, say, some of the heavier quarks that are a few GeV, all the way up to the top quark that has a mass of about, actually it's 172 GeV, so about 175 times the mass of the proton. So, the main takeaway from here is fundamental particles do have mass. The W and Z boson are not on here, but they are 80 and 90 G, approximately 80 and 90 GeV respectively, and just give you an idea of where they sit. Okay, one more thing before introducing the Higgs boson is symmetry. Symmetries are a vital part of particle physics because the standard model, the mathematics of the standard model, is based entirely on symmetries. And the symmetries, one result of it being based on symmetries is the fact that all fundamental particles are in fact required to be massless in order for the symmetries to be respected and the mathematics of the standard model to hold. However, we know that fundamental particles have mass, as I just showed you. So, for quite a while throughout the mid-20th century, this was one of the biggest questions in particle physics. How can you reconcile particle masses with the symmetries required by the standard model? And the answer is in the introduction of the Higgs field and spontaneous symmetry breaking. This was explored quite a bit by a large number of theorists in, I believe, the 50s and 60s, and ultimately it was Peter Higgs that kind of hit on something new, and so it has since been called the Higgs mechanism, although many other brilliant theorists all contributed to this. So the idea behind symmetry breaking is if you can design a system that has a symmetric, that has a symmetric state that is unstable, the system will spontaneously fall into a stable but a broken symmetry state. For example, if you stand a pencil up on end, it's symmetric, but it's unstable and will fall over quickly. And by picking some direction in which it falls, the symmetry is spontaneously broken. And so that's what's done with the Higgs mechanism. The Higgs mechanism introduces a field with a potential that looks like this, such that at the value of 0, where there is no, the value of the field is 0, the potential is at an unstable equilibrium. And the universe falls into a stable equilibrium at some point at some direction around this center point, and thereby breaking the symmetry. I won't go into the mathematics, but as a result of this, you actually are able to recover fundamental particle masses while still having a symmetric system. You introduce this idea that the symmetry gets broken spontaneously, and you can recover that. So the introduction, the field is a scalar field, typically denoted as phi, and the potential is written as this. It has two parameters that are important, mu squared and lambda. And this will be important later in my talk, but I just wanted to introduce the idea now. And if lambda is greater than 0 and mu squared is less than 0, you end up with this shape and you end up with the Higgs mechanism working. And you get spontaneous symmetry breaking. So, while the great thing about the Higgs mechanism is that it explains fundamental particle masses, and this is often described in another way as interactions of the particles with the Higgs field, but it also, the mechanism also predicts the Higgs boson. And so this is a neutral, an electrically neutral spin 0 particle. Spin 0 means it's a boson. And it couples to other particles proportional to their masses. And so the upshot of this is the prediction of the Higgs boson is a uniquely testable prediction of the Higgs mechanism. So if we can find the Higgs boson, well, at once upon a time, the question was, if we can find the Higgs boson, well, that would mean that we can confirm the Higgs mechanism. And so, well, spoilers, we did find it, but first I'm going to tell you a bit about experimental particle physics and how we go about performing the experiment and how we discovered the Higgs boson. So here's an analogy I'd like to use of how would, if you asked an experimental particle physicist how an alarm clock works, we would come up with an experiment to try to understand how it works. We'd smash it and look at what comes out of it. And so, you could imagine if you do this enough times, you'd see different parts coming out. Enough ways you could actually reconstruct, a model of what is actually going on the inside of the clock, and therefore reconstruct a model of how it actually works. So in particle physics, we do pretty much the same thing, but with small particles. So we start by accelerating beams of particles at nearly the speed of light. And these particles can be quite a few different types of particles. As long as they carry an electric charge, we can accelerate them. Most commonly, we use protons, electrons, or heavy nuclei, or rather, ions. You could also, accelerate positrons or antiprotons, or you could even accelerate muons. But for the most part, these are the most common types of particles we accelerate. And then we smash them together in hopes of finding new physics. And then if we create any new particles in these collisions, well, they most likely are very unstable, and they will likely be very massive, and that means they will very quickly decay into lighter, stable particles that we can then directly measure. But these measurements are, as simple as it is to smash things together, the measurements are not so simple. And so we use massive, complex detector systems to very precisely measure the remnants of these collisions. And then ultimately we take the data out of the detector to try to reconstruct what happens in the collisions. And then, very large numbers of physicists work together to try to find evidence of new physics in all of this data. Sometimes it's looking for new particles, sometimes it's trying to precisely measure some quantity that governs particle interactions to see if it deviates from what the standard model predictions are. So the machine we use is the Large Hadron Collider, and this is an accelerator located just outside of Geneva, Switzerland. It's a 17-mile long ring that's about 100 meters underground. So you can see it here. It crosses the border between Switzerland and France, and passes underneath primarily the French countryside. And in this ring, there are two beams of protons that circle the ring in opposite directions. Around the ring, protons, like any particle, left to its own devices, prefers to travel in a straight line. So in order to keep it in the ring, we use a series of about 1,200 superconducting dipole magnets located all around the ring that keep the beam, keep curving the beam to keep it in the accelerator. And these are superconducting, which means we have to cool them to about 1.9 Kelvin to reach superconductivity. This is this isn't the magnet itself, but this is an example of the housing of the magnets. So you can see how large these are, and we have 1,232 of them around the ring. So the protons travel at almost the speed of light, so we have something like 11,000 revolutions around the 17-mile ring every second. And then at 4 different interaction points, the beams cross, and we cross the beams and get collisions. Okay, just quick show of hands, who gets the reference? Okay. So I'm not as much of an old fogey as I'm afraid I am. I realize this is out of date. 6 million collisions per second. This was run 2. We are now running at about 2.4 billion proton-proton collisions every single second at each one of the 4 interaction points. And at each one of these interaction points exists a different experiment. These are ELISE, LHCb, CMS, and ATLAS. And ATLAS is the experiment I work on. So first I'll just say a couple words about ELISE and LHCb. ELISE is it's a Large Hadron Collider experiment, is what it stands for. It primarily focuses on collisions between heavy nuclei at the LHC. And the main purpose of it was to first observe and now continue just to study a new state of matter called quark-gluon plasma. Then LHCb is another targeted experiment that is trying to answer the question of why is there more matter than antimatter in the universe? Not naively, we would expect at the Big Bang, equal amounts of matter and antimatter would be created. but there's very clearly an asymmetry, and LHCb is trying to probe possible explanations of why that is through interactions involving the B quark. And then CMS and ATLAS are two general purpose detectors at the Large Hadron Collider that are designed to for a wide variety of physics measurements and searches for new particles. And arguably, were both designed specifically to find the Higgs boson. So the ATLAS collaboration, it's a very large collaboration. There are about order 3,000 grad students, postdocs, faculty, and research scientists all working together on this machine and to analyze the data. The latest count I found, it's made up of 182 institutions from 41 countries. It is a truly international effort, and the entire program is funded by the participating governments by way of the different institutions. Within the collaboration, all work is openly shared. I mean, there are always internal politics and such, but anyone in ATLAS has the right to get involved in any bit of work, any analysis that's ongoing there. And we have a lot of shared computing and code resources that we use for our analyses. But in order to be allowed to be on the collaboration and analyze data and publish results from this data, everyone is required to contribute to the operation of the experiment. Otherwise, we would not be able to run the experiment and collect the data we need. And then ultimately, in physics, our final result is our papers. And all ATLAS papers have every single author, every single member of ATLAS as an author, and therefore every member of ATLAS has the right to review and approve or comment on all papers that we publish. And yeah, we're all on the author list. I'm like on page 15 of 17. Last time I checked, it's a big list. And then here's just a map of all the different countries that are involved in ATLAS. Okay, classic picture, you've probably seen it. This is during the construction of ATLAS. To give you an idea of the scale, there's a guy, and now this is all filled in, but the most notable feature here are these toroid magnets. They actually show up in the ATLAS, the name of the ATLAS experiment, a toroidal LHC apparatus, named after the large toroidal magnets that are so distinctive. So, as I said, it is a general purpose detector that's designed to discover new particles and do other physics measurements. It's 25 meters tall and 44 meters long, and it's located about 100 meters underground, where along the LHC. And if you were to count up, it's order 100 million, maybe a few 100 million individual detectors throughout this machine. And good figure of matters, approximately 3,000 kilometers of copper wire go into the detector. While the LHC is running and providing collisions to ATLAS, this happens 24 hours a day during the periods in which we are collecting data, and therefore ATLAS is in operation 24 hours a day, so we can collect as much data as possible. And while it's running, all the detector systems have to be continually monitored to ensure data quality. So if we look a bit closer at the ATLAS detector, it's cylindrical in shape. It has the barrel region and the end cap regions. To give you a bit of an orientation, the beam line comes in this way and in this way, and the collisions happen right in the center at the interaction point. And but then if you look at the cutaway, there are layers of detectors. And these layers exist both in the barrel and along the end caps, so it's not as easy to see in the end caps. This centermost part of the detector is the tracker. This is a silicon-based tracker that allows you to detect charged particles passing through with extremely high spatial and temporal precision. Following the tracker, you have two layers of calorimeters, the electromagnetic calorimeter and the hadronic calorimeter. And then finally on the outside is the muon system. And so the muon system is made mostly of gaseous chambers that also detect charged particles passing through. Meanwhile, the calorimeters are designed to fully absorb and measure the energy of particles that enter them. So if we change our point of view and look down the beam line, you would see a circle. If we take a slice of it, this is a not to scale diagram of what you would see with the interaction point in the beam line right here. And as you go out through the different layers, you have your silicon detector, your pixel and strips, your transition radiation tracker, which is also part of the tracking system, your electromagnetic calorimeter, your hadronic calorimeter, and finally your muon system. And this is just to demonstrate how different particles are detected as they pass through the detector. Anything that has an electric charge is picked up in the inner tracker. So muons, protons, and electrons, you see the solid line passing through there. We're able to detect those, whereas anything that's electrically neutral is invisible to the tracker. Then anything that interacts electromagnetically, specifically photons and electrons, will shower and be fully absorbed in the electromagnetic calorimeter. Anything that interacts through the strong force or interacts hadronically, such as protons and neutrons, will be showered and fully absorbed in the hadronic calorimeter. In the meantime, muons make it all the way through and get picked up in the muon spectrometer. Neutrinos, on the other hand, are not seen at any point in the detector. Now, this is an overly simplified model just to show how we can make use of all the different components of the detector to detect and identify different particles as they pass through. Hadrons will deposit energy in the electromagnetic calorimeter. Electrons and neutrons will deposit energy in the hadronic calorimeter. It's not a clean split like that, but it's more or less the idea. Each one is optimized for a certain type of interaction. I also want to point out the fact that you may notice that all the charged particles have this curve in them, curving one way or another. This is the purpose of the toroidal magnets and also the solenoid magnets in the experiments. These provide very strong magnetic fields that cause the charged particles to deflect as they are radiating outwards. This deflection allows us to measure two things. One is the charge of the particle, whether it's a positive charge or a negative charge, and they all will have unit charge or 1/3 unit charge or 2/3 unit charge, and it will also tell us the mass over momentum ratio based on what the curvature is. And since these are all identified particles, we know the mass and therefore know we can accurately measure their momentum as well. So that's how we detect particles, and then we try to use them to reconstruct physics events that happen in the collisions. So now I need to introduce the idea of cross-sections before talking too much about physics events. So a cross-section is simply a measure of a probability in particle physics. Since this is a quantum system, anytime you collide two protons together or two of any particles together, it is completely random and non-deterministic what will happen. Things happen with well-defined probabilities, and we try to measure these, and we refer to these as cross-sections, and we measure them in units of picobarns or femtobarns. And so this is actually a summary of the measurements of all the atlas measurements of cross-sections of different processes occurring, where the cross-section of two protons interacting is about 500 microbarns. Cross-section of a W boson being produced is about 10 to the 5th, order 10 to the 5th picobarns. There's a Higgs boson, the total cross-section is about 20 picobarns. Much smaller than some of the other processes, but also much larger than other, even other ones. And so there's a very wide range of cross-sections, and once again, probabilities of something occurring in a collision. And so for finding the Higgs boson or anything else, well, typically your signal, is what we'll refer to the Higgs boson as, it's produced at a much lower rate than any of the other processes. And so the other processes are typically referred to as backgrounds because, well, we get far more, say, W bosons being produced than Higgs bosons. And if you're looking for a Higgs boson, you might have to deal with W events that produce W bosons to look for your signal on top of the background. And so about 1 in 10 to the 12 collisions gives you a Higgs boson. The other 10 to the 12 are the other events. And so if you want to find something like the Higgs boson, you need a lot of data. And we refer to this as luminosity. And that is the rate at which collisions occur and we collect the data. So some back of the envelope calculations. So every 25 nanoseconds, the LHC crosses bunches of protons. And each bunch of proton has about 10 to the 11 protons in it. And in each bunch crossing, we have something like 60 proton-proton interactions. And it takes about, since it takes about 10 billion collisions to produce one Higgs boson, do some quick calculations and say, at the LHC, we produce about one Higgs boson every 4 seconds. The other 10 billion collisions are background events that we need to distinguish the signal from. And so if we want to control how many Higgs bosons we produce, there are 2 LHC parameters that affect this. First is energy. Higher collision energies means that the higher the production cross-section for Higgs bosons increases. And then luminosity is the number of collisions. So if we get more collisions, we will have more opportunities to produce a Higgs boson. To give you an idea of how many we've produced so far, in 2011, we collected about 4.5 inverse femtobarns of data. Don't worry about the units. It's this convention we produced about 88,000 Higgs bosons. 2012, throughout the entire year, we produced about 470,000. And it was in 2012 was when we, halfway through 2012 is when we announced discovery. So we didn't even have the full 470,000 to do the discovery. And then between 2015 and 2018, we produced approximately over 7 million Higgs bosons across those years. But as I mentioned earlier, new physics, new particles are unstable. They quickly decay into lighter particles. Well, and so we cannot directly detect the Higgs boson. Instead, we can only detect its decay products. But similar to productions, particle decays are also completely random and non-deterministic. And so the best thing we can do is measure the probability of a Higgs boson decaying into different final states. Since the Higgs boson couples to particles proportional to their mass, this strongly affects what the branching ratios are, is what we refer to these decay probabilities. But also, we can also have decays to massless particles, such as the photon, through loops of heavy particles. And so the predicted branching ratios of the Higgs boson are shown here, with 57% of the time, the Higgs boson will decay into a pair of bottom quarks, and all the way down to 0.2% of the time you'll end up with 2 photons. And there's a wide range in between, and there are other decay modes that are even more rare. So there are a lot of different decay modes that we could use to look for Higgs bosons. And they all have different advantages and disadvantages, and some are just not usable. But 2 were used to discover the Higgs boson. And these both have the advantage of having very clean signatures that are easy to identify over background events. Since the discovery, other decay modes have been observed, and are very important for measuring different properties of the Higgs boson. But the 2 that I'll talk about and were used for the discovery are Higgs to 2 photons, which simply looks like 2 high-energy photons in your detector, and the Higgs to 2 Z bosons further decaying into 4 leptons, either electrons or muons. This looks like 4 high-momentum electrons or muons in the detector, such that you can pair them together and reconstruct Z bosons. So I'm going to play a video here of actually the accumulation of data that led to the discovery of the Higgs boson. And this is in the diphoton channel. This is the channel with 2 photons where we can take the photons with some relativistic mathematics, add them together, and calculate what is known as a diphoton invariant mass. And so we'll plot all of the events in this histogram with the x-axis being a diphoton invariant mass. As it runs, you'll see the accumulation of data creating some kind of falling spectrum. And this, and then there will be a blue line to it, and that is what fit to it, and that is what you expect if there is no Higgs boson. But if there is a Higgs boson, we'll begin to see an excess over the blue line and a localized bump. And so this is actually data accumulating through 2011 and 2012. And as you can see, there's a bit of a bump forming here right in the middle at about 125 GeV until we accumulated enough that we can say this is a statistically significant excess localized at 125 GeV. That corresponds to the Higgs boson. You can see the data points, the black points, they fluctuate around the smooth blue curve. And that's to be expected. This is a purely statistical process. And so any single bin giving you an excess over the background prediction is not enough to make claim discovery unless you're at UA1 or UA2. Sorry, bad joke. But if you have a coherent excess here, we can do some statistical analysis and make a statement that this is indeed statistically significant enough to claim discovery. And then if we look at the other channel that I mentioned, the 4-lepton channel, we see something similar where we can do the 4-lepton invariant mass. The distribution looks very different because the background processes are different. But we're comparing the data points to the red and purple background. And over time, we collect enough data that we see this excess in data over the backgrounds right here, right around 125 GeV. So through this other decay mode, we can further confirm the existence of a boson that decays that has a mass of 125 GeV. So there's the zoom in and looking at the simulated background compared to the data. Okay, and so yeah, that was the discovery of the Higgs boson. It truly was finding a needle in a haystack with large backgrounds, and we ultimately discovered the Higgs boson. We announced the discovery on July 4th, 2012, and at CERN we refer to it as Higgs Dependence Day. And so Atlas and CMS simultaneously observed it with 4-point-something significance, and then when we combined the two results, we passed the 5 sigma significance, which is the threshold that we set for ourselves for actually claiming discovery. Okay, I'll just say a few things about working, what it's like to work as a particle physicist, and then I'll get into my own research. I think if I still have time, okay. So CERN is a great place to work. It's a place where we work hard and play hard. It is, well, more so pre-COVID than post-COVID. It is a very vibrant place filled with people. It's slowly getting back to its pre-COVID levels. Everyone's there working together. All work is done in English, so you can communicate with people from all over the world. And a lot of people collaborate. We have a lot of meetings. We discuss ideas. It's really a really wonderful place to work, and a lot of innovation goes on there. When doing work at CERN, you can do things like outreach. I give a lot of public lectures, something I particularly enjoy doing. You can work as a tour guide at CERN. You can meet people like Stephen Hawking. That was several years ago before he passed away. I've worked as an underground tour guide. There I am as an underground tour guide. There's my wife actually on our first dates. She came over to CERN. I gave her a tour of the Atlas cavern. We also do service work. As I mentioned, you have to do a lot to keep the detector running. Everyone contributes to building and running the detector. So we're required to do this to work in the collaboration. you can do a lot of work designing new detector systems and the electronics for it. There's also a lot of development of software for to allow you to test and run the new detectors. And then physics analysis. This is what most people are most interested in, is analyzing data to look for new physics, to go through all of the huge amount of data to look for evidence of new physics. We do a lot of coding. It's mostly in C++ and Python. Yeah, and I'll get to details about this in just a little bit because that is the work I'm most interested in. So, getting into my research interests. So I'm going to go back a little bit to the shape of the Higgs field. So if you remember that, and the Higgs field looks like this with the two parameters mu squared and lambda. And remember, if lambda is greater than 0 and mu squared is less than 0, the Higgs mechanism can work. So, well, we actually have a very good measurement of mu squared, but what if we could measure lambda directly? Then we would have a very good idea of the, much better idea of what the Higgs field is like, what its potential is. And so my goal is to measure lambda. And as it turns out, this lambda shows up in the Higgs boson self-coupling. So this is just a piece of a Feynman diagram showing the coupling between 3 Higgs bosons. And the strength of this coupling is proportional to lambda, which is the same lambda that shows up in the Higgs potential. I don't know when the computer seems to be frozen. Okay. Yeah, so we're looking to measure this self-coupling so we can measure lambda. And it's always nice if lambda does equal the standard model prediction. If it doesn't, well then actually, in my opinion, is much more interesting because that requires the theorists to come up with an explanation, and it's the way forward to learn more about the universe and maybe explain a few more things. Let's see if this works. Okay. So the way we look for lambda is we look for the production of 2 Higgs bosons at the same time. As hard as it was to find the Higgs boson, finding 2 Higgs bosons is much, much harder. There are two Feynman diagrams that contribute to the production of the Higgs boson. The one on the left that we refer to as the trilinear diagram or the triangle diagram includes this Higgs to 2 Higgs coupling and this modifier that we call kappa lambda. If you ignore everything to the right, this is just the production of a single Higgs boson. And then through this coupling, it can give you 2 Higgs bosons. And so this is what we're trying to observe. However, in the standard model, there's another production mode that does not include this trilinear coupling. We refer to it as the box diagram, where you can produce 2 Higgs bosons just through their couplings to fermions. This is primarily top quarks. And these 2 diagrams have a relative negative sign between them, which means that they interfere destructively, which is a bit unfortunate because it results in a cross-section that's 1,000 times smaller than that of a production of a single Higgs boson. This makes it quite difficult to find. So looking for this, this is all messed up. Okay, so just like in the diphoton invariant mass, we can take the 2 photons, add them together, and get a mass. Well, we can do the same thing. If we can measure 2 Higgs bosons, we can add them together mathematically to get a value that we refer to as the di-Higgs invariant mass. As it turns out, actually, the 2 different diagrams contribute to different parts of the mass spectrum that we expect. So the standard model prediction gives us something, and this is a cartoon of course, but this is fairly accurate of what the distribution of di-Higgs invariant masses would look like, or are expected to look like in the standard model. Now the 2 diagrams contribute to to 2 different parts of this distribution. I will just say that So the point about that actually is if the lambda is different than the standard model prediction, the total cross-section can in fact be a lot larger than the prediction, but also it would change the shape of the di-Higgs invariant mass spectrum. And so that is one possible handle we have to measure if lambda is different. Okay, but looking at the cross-sections, this is the same plot that I showed before. Di-Higgs is down here. It's 3 orders of magnitude smaller than single Higgs. That's the main reason it is so hard to find. We haven't found it yet. Okay, so with the very tiny cross-section we cannot be wasteful. We have to use many different decay modes, many different final states to search for Higgs boson pairs. We need to use all possible events that we can find. And this maximizes our chances of finding it. Since I showed you all the different decay ways a Higgs boson can decay, well, if you have 2 Higgs bosons, their decays are completely uncorrelated from each other, and so you can have any combination of these different decays, such as 4 B quarks, or 2 B quarks and 2 tau leptons, or 2 B quarks and 2 photons, or 2 B quarks and 2 Ws, or 4 Zs, or any combination here. I'm only going to go through 3 of these decay modes: the 4B, the BB tau tau, and BB gamma gamma decay modes, because these are the 3 most sensitive channels in searching for Higgs boson pair production. And I'm not going to go into too much detail because we do have limited time. I'm happy to talk more later. But in the 4B channel, both Higgs bosons decay into B quarks, and through the process of parton fragmentation and hadronization, you can't see quarks directly. Instead, they show up in the detector as what we call hadronic jets, very large sprays of stable hadrons that come from the initiating quark. And we have techniques of identifying whether a jet comes from a B quark or a different type of quark. And so if we look in the 4B channel, we're looking for events that look like this, with 4 jets that are identified as coming from B quarks, and that can also be reconstructed to be consistent with a Higgs boson. Two different pairs of them being reconstructed as Higgs bosons. You can also look in the BB tau tau channel. Similar to the 4B channel, you end up with a couple of jets. These are the jets here in blue, and then 2 tau leptons. So tau leptons are not stable. We do not detect them directly. They also decay, and can either decay leptonically or hadronically. If a tau lepton decays hadronically, it shows up in the detector, looks a lot like a hadronic jet. We are able to identify them, distinguish them from quark and gluon initiated hadronic jets fairly well. Or it can decay leptonically and give us either an electron or a muon along with a couple of neutrinos. So in this particular event, we see 2B jets, a hadronic tau decay, and a muon. So this is another candidate event for Higgs boson pair production. And then finally, the BB gamma gamma, once again, 2B tag jets, and much more simply, 2 photons that show up in the detector. These 3 images are just simply renderings of the 3-dimensional events that we try to use to demonstrate what the events actually look like. So in each one of these 3 channels, we're dealing with very different event properties and very different types of background events that we're trying to distinguish from. So each one of these uses a wide variety of different techniques. We do a lot of machine learning techniques, a lot of unique object reconstruction techniques, and then the background estimate techniques vary widely, whether we're using Monte Carlo simulated background events or using actual data actual data to estimate the backgrounds in the regions that we are actually looking at. Well, we have not found Higgs boson pair production yet, but we can say how well we haven't found it. So what we do is we set limits. And setting a limit, well, a limit is a statement about, well, colloquially, how well we haven't found it, but more accurately, what is the maximum value a parameter can have such that it could exist, that we would not have seen it yet in the data that we have collected. And so these are somewhat complex plots to read, but if we just look at this over here, the x-axis is the upper limit with a 95% confidence level. Everything is, statistical. We can only make a statement with certain confidence intervals. The limit of the cross-section divided by the standard model prediction, such that 1 is the standard model prediction, and anything above 1 is, well, not the standard model. This is just much easier. If we're aiming for 1, it just makes things easier for us. And so this first row is the BB gamma gamma limits alone. And this dashed black line is the expected limit. Without looking at the data, just looking at how the analysis is designed, how well we expect to what level we expect to be sensitive to this process. And so the expected is at 5.7 times the standard model. The turquoise and yellow bands are uncertainties on this, 1 and 2 sigma uncertainties. And then the solid black line is after we look at the data, what is the limit we can set. So across these 3 different channels, we have different sensitivities, different expected limits and observed limits. But then we can statistically combine the results from these different channels to get an even stronger limit. And so the combined one is down here on the bottom with, right now our observed limit, upper limit is 2.4 times the standard model. So we're still a little ways away from reaching the value that the standard model predicts, which is by definition 1. But we're going to continue working as we get more data. We continue these analyses. We get more data that makes us more sensitive, but we also continue improving our analysis design and our experimental techniques that will keep pushing this closer and closer to 1 until we actually observe Higgs boson pair production. Then on the other side, this is another type of limit where we set limits, we constrain the possible values of lambda. We use this, we put it in terms of kappa lambda, which is the actual lambda value divided by the standard model prediction. So once again, the standard model predicts a value of 1. It's so much easier to deal with. And the way this can be read is this red line is the cross-section as a function of kappa lambda, where the standard model is here. And if lambda gets very big, or very negative or very positive, the cross-section can be much, much higher than the standard model prediction, such that maybe we would have already observed it. And with that, we can actually set limits on anything below this point where the red crosses the black. Anything below there is excluded, and anything above this point is also excluded, whereas lambda, experimentally can still exist within this range that we have not yet excluded. Yeah, and so that is everything I have. Sorry, almost everything I have. I often get asked, how do you do this if you want to pursue a career in this field? First and foremost, you need to be very, very passionate about physics. Then you need to go to graduate school. And I should clarify, if you want to pursue a career in particle physics, you need to go to graduate school. Graduate school is a massive commitment. It is not for everyone. You have to know you want to do it. It's 6 years of your life dedicated to studying this, and definitely not making much money. And then the single most important thing is learn how to program. It is never too early to start learning how to program. It doesn't matter if you're learning C++, Python, or any other language. The first language is the most difficult to learn, and from there you can translate. And it is an invaluable skill in particle physics, all throughout STEM, and also I'm pretty sure elsewhere in the world, though I don't have so much experience outside of physics. So that is actually my #1 piece of advice. And also, if you do pursue this career, do not get discouraged. It's easy to get discouraged in grad school. There's a lot of background information you have to master. It takes a lot of repetition to get it. And then doing the unique cutting edge research, this can be also very discouraging, but can very much be worth it. So if you want to do it, don't let it discourage you. Definitely hang in there. And then finally, why do we study particle physics? Because we have an insatiable thirst to understand the universe we live in, and it is fun to smash things.
All right, now we have time for some questions.
I have two simple questions, I guess. How thick is the proton beam, or whatever beam we're using?
The actual spatial space, it'll be something on the order of a few micrometers, I believe. Yeah, it's very compact, and it's going to vary whether you're in the beam line, around the beam, or at the collision points. The accelerator people, which I'm not an accelerated version, they have incredible fine control over the beams. They can compress them and steer them into the collisions at the collision point. Otherwise, so for most of the beam line, they're actually in separate pipes, but at the collision point, they're able to steer them into a very, very small space I don't order, micrometers.
And then, my knowledge of at least older particle physics was they had the cloud chambers and they saw spinning tracks. I know you said that they were just animations and they don't represent exactly what's going on, but it looked like everything was just a straight deflection. So you guys ignore.
So if we go back to dB tau tau,
yeah,
and this is going to be a very high momentum tau. So there is some level of curvature to that, and it could honestly be somewhat masked by the particular projection that's being used here, but there is nonetheless some level degree of curvature, and so we are able to measure the momentum of that.
just the scale of these detectors doesn't give enough time.
I'm sorry?
The scale of the detectors doesn't give enough time to start curving.
Yeah, and that's one of the reasons it is so large. If you want to, for a high energy, high momentum muon, if you want to measure its momentum with any kind of good resolution, you've got two options: not an extremely strong magnetic field or an extremely long, extremely big detector. In Atlas, we had more space, so we went with a larger detector. CMS, they have a smaller cavern, so their solenoid magnet is 2 or 3 times, provides a 2 or 3 times stronger magnetic field than our toroids.
Okay, thank you.
You're very well.
Can you show your results slide one more time?
Yes.
Yeah, so can you frame kind of those observed versus expected? First question is that integrated luminosity, how much more data do you have right now compared to that?
Compared to this, we have about 3 inverse femtobarns more, because this is the full Run 2 data set. And Run 3 has had a pretty pathetic start so far. We've had quite a few machine issues. We're probably expecting more like 30 inverse femtobarns this year, and so far, last I heard, we collected about 3. So we have not yet combined with Run 2, but that's only 20 inverse femtobarns. That's not going to add very much. But by the time we get done with Run 3, which started this year and will run through 2025, unless there's a possibility it might get shortened or extended by a year. There are a lot of factors that go into that. We are expecting order 300 to 450 inverse femtobarns, so 2 to 3 times as much data.
Perfect. So now the numbers you quoted there, is 3 times more data enough to get signal then?
So, official party line, no. We expect to see it in the high luminosity LHC, in which we expect to collect somewhere between 3,000 and 4,000 inverse femtobarns, an order of magnitude more. Unofficially, every time we have done projections from our latest and greatest measurements to where we'll be with more data, we have significantly exceeded the expectations, such that if you use that kind of optimistic hand-waving arguments, we halfway expect to be on the threshold of observation at the end of run 3. It could go either way. It is definitely possible, but it also then leads to assuming standard model, there's no guarantee, but we're pretty much guaranteed to observe it by the end of the high Lumi LHC.
Thank you.
Yes.
I already asked one, so.
Okay. So yeah, from the current data, we expect like 8 million Higgs, right?
Yeah,
So the expectation is a double Higgs is like 1,000 times less.
Yes.
And what's the uncertainty in this estimate?
The uncertainty on like how many
1,000, yeah. 1,000 less than single Higgs. What's the uncertainty on this?
so the uncertainty on the theoretical cross-section, order 20% uncertainty on that we use for our theory uncertainties, and this primarily comes from calculations based on the top quark mass in the loop in the calculations. That's our single largest uncertainty. If the theorists can resolve that, we can have uncertainties down to just a few percent. But we're still waiting. Yes.
What's a barn?
So
Besides something you put animals in.
what was that?
Besides something you put animals in.
Yeah. So I'm actually forgetting what the conversion from barn to square meter is, but
10 to the minus 24 centimeters squared.
10 to the minus 24 square centimeters.
Yes.
Yeah. Okay. Yeah. Thank you.
1 volt.
And it originally came from early nuclear measurement of some cross section, and it was much higher than anecdotally. It was much higher than was expected, and someone's like, "Well, that's as big as a barn," and it kind of stuck. There are actually people have tried to introduce additional units relating to the barn, like the shed and the outhouse that get smaller and smaller. They're not in common use. Yes.
So when you say you have 5 inverse barns of data left, what is that?
Excellent question. It's a weird unit, and I've heard so many people complain about it that are outside of the field. It's a unit of convenience. The reason we define the amount of data we have in terms of inverse femtobarns is, let's say I have a process with a predicted cross-section of 5 femtobarns, and I've collected 100 femtobarns of data, inverse femtobarns of data. I can quickly tell you I expect to have produced 500 of those events. The units cancel, multiply your cross-section times your amount of your integrated luminosity, and you have your number of events. Okay. Physicists, particle physicists, we prefer units of convenience. It has very little sensical use outside of what we do. If I go back, refer back to my very first slide about units, we measure mass, energy, and momentum in GeV. It's really actually GeV for energy, GeV per c, divided by c, speed of light for momentum, and GeV divided by c squared for mass. But we're lazy, we say c equals 1. And so everything is just in GeV. Then we can just convert mass to energy very quickly.
I was kind of curious, how did you calculate the expected limit on these values?
So the expected limit, we build our background model typically with using simulated processes, and then we build what is known as an Asimov data set that is built from the background model, and we say, well, if the data set is equal to the background model, with what statistical precision can we exclude this? And then with all of our estimated systematic uncertainties. And then we look at the data and then set the observed limits. So it didn't used to be this way in particle physics. I don't know the full history of it, but nowadays we use a process, we have a procedure of doing blinded analyses where we do not look at our data until we have set our analysis in stone. That way we do not bias ourselves by, it's very easy to, well, it looks like it might be an excess, let me tweak this, let me tweak this. Oh, suddenly I have an excess in data over Monte Carlo because I kind of forced there to be one. Yes.
So your reference to UA1, was that a dig at Rubio?
Yes, it was a dig at Rubio.
Discovering something at this scale, oh, it went away, and at this scale, at this scale. You might want to tell the story. It's kind of
I don't know the full story. I just know he was claiming discovery off of a single, a discovery of, I think it was the W off of a single event.
Yeah.
Though I don't know the full story, so I apologize. Maybe I can put you on the spot.
So Carlo Rubio, a great physicist and a famous guy, but he always wanted to be first, and so what he would do, if there was any kind of hint, he would say, oh, it's a discovery. And then if it was, then he was like, oh, see? And then if it went away, then he would be, everyone would forget. Except I guess not everyone forgot, because there's still this sort of story where, it's like, if you're a 5-year-old, you want to claim stuff and you lick it, that's the same idea. All right, anyway, any other comments, questions? All right, let's thank Dr. Veatch for a great talk.